of Applied Energy Research here in Lexington. Originally announced speech by Ushi will, I think, be the first one in the afternoon session.
Yes.
Okay, please go ahead. Thanks.
Thank you. Let's see if mine is.
No, you've got a problem. No.
Thanks. Yeah, I'm with the Catalyst Research and Testing Center, which is, as Jürgen said, part of the University of Kentucky Center for Applied Energy Research. And today I'm going to talk about a collaborative work with my co-workers at the CAER and my supervisor, Dr. Burke Davis. And it's also in the area of hydrogen production, and we're looking at metal-promoted Syria catalysts to do low-temperature water-gas shift. These catalysts have been found to give very high activity for water-gas shift in comparison with the copper-zinc oxide catalysts, which are typical commercial catalysts available today. And most of the talk will be centered on the mechanism of the reaction and some of the techniques that we're using to try to understand how these catalysts operate. So I'm going to briefly review the proposed mechanisms that you can find in the literature, and then I'm going to talk about ways that we've devised, methods that we've devised to try to validate an appropriate mechanism. And the reason is we're trying to understand what is the active site at work on these catalysts, and once we know that, then we can try to develop more stable catalysts by stabilizing the active site. So we prepared a series of catalysts at different studies where we're trying to gain specific information from those catalyst series. Pretty much covered that. And water-gas shift reactor, of course, is downstream from steam reforming and partial oxidation reactors. And it's basically a staged process. High temperature shift is typically run at near equilibrium first, which converts the 8 to 10% CO after reforming down to about 3 to 5%. And then low temperature shift is needed because high temperature shift is operating where you have some equilibrium limitations. So we need to really move to a low temperature regime if we're going to achieve high CO removal efficiencies. Of course, when you move to low temperature, you need a very active and effective catalyst. And then that will convert the CO down to about 0.3 to 0.5%, and then a proc system, preferential oxidation, should handle the rest of the CO. You can see it's slightly or somewhat exothermic reaction there. Let me go over the two mechanisms that have been proposed. The most well-received mechanism is a Syria-mediated redox process. You'll find this in a lot of the review literature. And in this mechanism, adsorbed CO on the metal reacts at the interface with Syria to reduce the Syria surface and generate CO2. Then water comes in and reacts with the reduced Syria surface and basically replenishes the oxygen vacancy to give you hydrogen. So the active site there is the platinum-Syria interface. An earlier mechanism was proposed by Shido and Iwasawa. Here, reduction of the Syria is also very important. And the role of the metal actually is to catalyze the surface reduction of Syria. Once that's done, you have geminal OH groups that form on the Syria surface, and reaction of the geminal OH groups with CO forms formates on the surface. And these are the proposed intermediates for the reaction. And we go through this transition complex with water, This is proposed to be the rate-limiting step, the decomposition of the formate with water to liberate hydrogen. And then we go through an unidentate carbonate, which releases the CO2 to complete the catalytic cycle. Kinetics have been studied very well in literature by a couple of groups, and they've proposed this rate expression. And basically, at high CO to water partial pressure ratios, the reaction's been found to be zero order in CO, first order in water. And at high water to CO ratios, which you would find in a typical fuel processor, reaction is first order in CO, zero order in water. And this has important implications for the surface coverages of the CO intermediate, which is what we're going to actually try to examine in our work. Under zero order, the adsorbed CO intermediate should be close to saturation on the surface. And under the first order regime, high water CO, the adsorbed CO intermediate should move to sparser coverages with the water gas shift rate. So it should become more reaction rate limited. Evidence for these two mechanisms. Folks who proposed the Syria mediated redox mechanism, they conducted their water gas shift studies really at a high CO to water ratio, and they observed the zero order. And in the IR, they found that the metal was close to saturation with CO. So they proposed on that basis that the metal was very important for the mechanism, whereas in the other mechanism, the metal just catalyzes the reduction of the Syria. And they found that OCO stretching vibrations that they observed in their spectra were likely due to carbonates, not formates, as proposed by Shido and Iwasawa. And evidence for the formate intermediate mechanism has mainly come from DRIFTS and TPD investigations. Now we've revisited the use of DRIFTS. DRIFTS is a nice technique because you can use loose powders and avoid diffusion limitations as opposed to pressing a wafer to do your IR work. And we have available a flow cell which we used for our studies. This is a diagram of our setup. We have the feed gases here, hydrogen and CO and nitrogen. We're scrubbing those with water and oxygen traps. They're ultra high purity, but just to remove any traces. And also iron carbonyl traps on the CO. And we control the gases with mass flow controllers. We can bring online a steam generator, and we heat trace all of our lines. We sometimes employ a booster reactor after the IR cell to increase the conversion levels, and we can monitor reaction products with a GC after we knock out the water. So some of the vibrations we are going to be interested in this work are for the formates and carbonates, the symmetric and asymmetric stretching vibrations, and then for linear molecules like the OH groups on the surface, as well as the CH group of the formate. So just keep those in mind. So in our first study, and I presented this actually last year, we were trying to find out which adsorbed CO species was rate limited on the surface. And we were using, of course, a high water to CO ratio, and we prepared Syria, fairly low surface area, by decomposition of cerium nitrate, and we loaded the Syria with 0.6% platinum. And just to recap that work, we reduced the catalyst first into hydrogen, and we observed during the reduction a decrease in this band here. That's in the OCO stretching region. There's no CH band associated with that, so we believe it it has to do with the decomposition of a carbonate. And we also saw some Syria CO and platinum CO appearing consistent with that. And most importantly, after the surface is reduced, you can see quite clearly the formation of the general OH groups on the surface of the catalyst. Those have been proposed to be the active site for the formate mechanism. Adsorption of CO to the reduced platinum Syria catalyst. This is after reduction, and then after adsorption of CO. You can see we have a number of bands forming in the spectrum. These are OCO bands, which are consistent with the OCO stretching assignments of formates, not carbonates. And accompanying those bands, we see very pronounced CH stretching bands, also consistent with formates. And we see a decrease in the general OH groups there. And the spectra is very similar to adsorption of the formic acid there. And also we found that these bands that we correlate to the formates all responded in a very similar manner under the water-gas shift reaction. And looking at which species is rate limited on the surface, this is platinum CO. Very little change over the range of conversion, water-gas shift rate, the CO conversion, whereas the formate becomes much more limited on the surface. Here you can see the dark band is the adsorption of CO alone, and the red is when we've replaced inert balancing gas, nitrogen, we're running CO and nitrogen with water to keep the CO partial pressure constant. And at low temperatures where the rate is low, there's very little change in the formate band, but as you move to higher temperatures and higher conversions, you can see that that band becomes much more reaction rate limited. Here's the CO, adsorption of CO alone. This is under water-gas shift. In contrast, if you look at platinum CO, there's very little change in coverage. This is under the first order condition. So the work was consistent with the formate mechanism. The platinum improves the reducibility of surface Syria, which is necessary to form the geminal OH groups on the surface. So we thought that with this knowledge, more active catalysts could be prepared by increasing the Syria surface area. The metal function would be then to promote the reduction of the surface. Interestingly, we looked in the literature, and we saw in a previous work the metal function had been explored. In this case, it was copper, and varying the loading from 5 to 40% copper showed no change in the water-gas shift rate, which would be consistent with the redox mechanism. Too far. So we prepared series with different surface areas, a medium surface area material by homogeneous precipitation of cerium nitrate with ammonia. And then we looked at a nanostructuring method by Lee and others. And in this case, urea is added to suppress the rate of precipitation. And we developed higher surface area series with that technique. We also co-precipitated zirconia and lanthanum into the Syria. And for the lower surface area supports, we sintered Syria at various temperatures prior to loading with platinum. And you can see the range of surface areas that we achieved with those methods. Actually, we now have a Syria which is much higher than this one, about 105 meters squared per gram, which I'll talk about later. And here you can see we did some XRD work, and we used the integral breadth method to try and figure out what the domain sizes were for these materials. We got a nice trend with increasing surface area. Of course, you have a smaller Syria domain size. TPR gives us some interesting information, but you have to be a little bit careful interpreting it. Basically, on Syria, you see two peaks in the reduction. You see reduction of the surface Syria, where you have removal of the surface capping oxygen atoms, and then the reduction of bulk Syria occurs at much higher temperatures. So on a centered one, you only see the bulk. On the higher surface area materials, you can see the reduction of surface Syria. Why I say we have to be careful is we did see that evolution of that CO from the decomposition of that carbonate, and so that should accompany the surface reduction of Syria. And platinum, addition of platinum catalyzes a reduction of the surface Syria to much lower temperatures, but affects very little the bulk Syria. And we tried to quantify that better by looking at oxygen uptake measurements on these catalysts after reduction at 300 degrees. You can see the higher surface area materials consume much more oxygen as you would expect. But more importantly, we're trying to find out if the formates can be useful to probe the active sites, that is the general OH groups, after reacting with CO. You can see absorbing CO on the catalyst as you move to higher surface areas. You have dramatic increase in the formate bands present on the surface. You can see the CH here and the OCO stretching vibrations here. The platinum changes very little, and we actually use that platinum CO to calibrate those formates, which I'll show later. And with all the catalysts that we prepared, the surface formates were reaction rate limited. You can see the high surface area here. This is at 250, 300, and 350. This is absorption of CO alone. This is under water gas shift. As you go to higher temperature, the band becomes much more limited on the surface coverage. Fixed bed reactor testing, we had a very nice trend increasing the surface area, increased the activity considerably in the fixed bed reactor. And if you take the formate to platinum CO intensity ratio and you plot it versus the conversion, you have a nice direct correlation, which really strongly suggests that the active sites are on the Syria, the OH groups. However, we didn't rule out the possibility of the Syria-mediated redox process, but we had to go to other techniques to try to probe the redox properties of these catalysts. So we looked at XANES, and we constructed an in situ ZAF cell. And these tests were conducted at the synchrotron at Brookhaven. And we looked at the L3 edge of cerium. I'm going to show you two references which we use for cerium plus 3 and cerium plus 4 carbonate and Syria. And we looked at unpromoted, platinum promoted, and gold promoted Syria catalysts. And we treated the catalysts with hydrogen to see if we could observe any change due to the surface reduction of Syria. And then we added water into the feed to see if we could if there was any evidence of reoxidation of the Syria by water in the presence of hydrogen. And that would be required to substantiate the Syria redox mechanism. So to look at the TPR, again, we have to be careful interpreting. But this is with 105 meters squared per gram Syria. This is unpromoted Syria, so this is reduction of the surface and the bulk. And then the platinum catalyzes a reduction to low temperature, and the gold even more so. So we were very interested in the gold catalyst. Here's the reference spectra in XANES, and we're looking at absorption of electrons into the unoccupied 5D levels. And this peak is usually labeled C, and that has to do with absorption into the 5D where there's no occupancy in the 4F, either in the initial or the final state. And this peak is typically labeled B1, and that has to do with absorption in the 5D where there's occupancy in the 4F in the initial state. This is B0 peak, and that's absorption into the 5D where there's some occupancy in the 4F in the initial state. But anyway, you can use these as references to figure out how much reduction there is on your catalyst. So here's our catalyst, unpromoted Syria at room temperature, and here we've treated it in hydrogen. And you can see that when you get up to 400, 500 range, just as you saw in the TPR, there is some change there, very important change for the surface reduction of Syria. And when you put platinum or gold on there, this platinum catalyzes the surface reduction to lower temperatures, you can see there. And here's our experiment where we tried to reoxidize the Syria with water in there. And we were flowing this for like an hour at each condition, and we saw absolutely no evidence of reoxidation of the surface Syria with the water. And we had a fairly high flow rate of water. I think it's listed on the next slide. The only evidence that we ever did see a reoxidation of Syria with water was just water alone with helium, and that was at 350 degrees, and it was very small change. And here you can see we did a linear combination fit with the references. Very little change under all conditions except helium and water with platinum. Going back to this slide, though, I just want to point out that the extent of reduction was much more important for platinum than for gold, as you can see there. And we went back and looked at those in the drifts, because at platinum, if the extent of surface reduction with the platinum catalyst is higher, then you expect to see more formates. And indeed, that was the case. For the platinum catalyst, we saw the formates at a much higher intensity than with gold. With unpromoted at this low temperature, you have very little reduction, so you see hardly anything. It's sort of a reference. And we tested the catalyst in the fixed bed reactor, and the platinum catalyst was found to be about 20 times more active than the gold. And then finally, to test the formate mechanism again, we looked at Kinetic to see if there was a kinetic isotope effect. And this had been claimed by Shido and Iwasawa back in the early 90s, where they ran the reaction with H-formate and water, and they ended up with this rate constant here. And then switching to the deuterated formate with deuterated water, the rate was found to decrease. So a normal isotope effect like that is associated with the fact that the CV bond is more stable than the CH bond, lower energy. It's about a 1.2 kcal per mole difference. So just to show you that we did manage to form the general OH groups as well as the general OD groups on the surface. And then this is a comparison under water gas shift, CO alone and under water gas shift for the surface formates and the deuterated formate. You can see the surface formate with hydrogen is much more reaction limited, rate limited than with deuterated water, which suggests kinetic isotope effect. And we also saw that the CO2 production with water instead of deuterated water, CO2 production was higher. And then we put some catalyst in the booster reactor after the IR cell, and we took GC measurements, and you can see there's a clear kinetic isotope effect when you switch from water to deuterated water. And then we, just to double check, we put the 50-50 mixture in there, and we got an intermediate value. So the kinetic isotope effect was found to be close to about 1.4 ratio of rates. And the difference in surface coverages was also about 1.4. So this is consistent then with the rate limiting step being associated with decomposition of the formate, which gives more evidence to the formate mechanism. So direction for future research, now we're focusing on the deactivation of these catalysts, trying to stabilize the active sites. And so the Syria surface is critical for the catalyst stability. And we're looking at putting refractory materials, co-precipitating with materials into the Syria framework. We've been looking at a number of different lanthanides as well as zirconium. Because we're claiming that the active site is on the Syria and the platinum really doesn't participate directly in the mechanism. Rather, the metal function is to catalyze the reduction of Syria to give you those active OH groups on the surface. So can other less expensive metals be substituted for platinum? Well, we have a poster on that presented by Emily Chenu in the poster session. And we've looked at a number of different metals, and we try to be fair, so we've tested these at an equivalent atomic loading. And finally, I'd like to acknowledge my co-workers, also Gerald Thomas, who helped me with the XRD. Bob Keogh helped me with the GC setup. Joel Young is a machinist who works in the physics department at University of Oklahoma. He helped build our ZAF cell, and Saeed Khalid helped us with the ZAFs experiments. And with that, I'd be happy to try to answer any questions.
Open for discussion.
After your initial test, have you gone back in and looked with your high temperature or high surface area Syria? Have you remeasured the surface area after you've taken them through some of those high temperature tests?
No, we haven't, but we plan on doing just that. You know, after we need to get into the deactivation, you know, the catalyst, and stability testing will be next. And we'll certainly be looking at the decline in the BET surface area, because that has been reported by Johnson Matthey to be the most likely cause of the deactivation of these catalysts. I don't believe it's over-reduction of the surface, which has been reported in a recent article. I think it is probably more linked to the surface area of the Syria. Certainly would be consistent with our active site.
I had one question that what preparation method did you apply for the preparation of the cerium oxide with the various surface areas? How did you modify that? How did you do that?
Well, there's a very nice paper by Marie Flitzani-Stephanopoulos' group, where they used urea to slow down the formation of ammonia and to slow down the rate of precipitation of the cerium nitrate in solution.
With that method, you've been able to modify the cerium oxide surface area from 5 to 105 square meters?
Well, we basically just ended up with the same surface areas that they ended up with, and we haven't devised techniques to go higher than that at this time. So 105 is about our limit right now. But we have prepared catalysts with the different refractory materials co-precipitated into the Syria, but we have not had a chance to test those yet. So.
When you dope, put a platinum on the cerium, and you see the reduction temperature is much lower.
Yes.
Have you observed that the platinum itself reduced, or just the support cerium reduced?
Well, we're using very low loadings of platinum, so after you have the reduction of platinum, you then have probably spillover to the Syria surface, which helps to catalyze the reduction in the Syria surface. So the two will be almost at the same point in our TPR. So basically the Syria surface would swamp out the signal of the platinum reduction. But we should go back and look at platinum reduction in the XANES. We should, go back to the platinum edge, the L3 edge, and look at the reduction in platinum as well. And hopefully we'll do that in the near future.
There are no more questions. I would like to thank you again. Thank you.